This is Catherine Nightingale with Chattanooga State Community College, and this video is for Math 2110 Calculus 3 on section 13.1. This is the second video for this section. You should have already watched the video titled Functions of Several Variables. In this video, we'll talk about level curves and level surfaces of functions with several variables. To start, let's look at what it means to be a level curve. A level curve of some function f of xy is the set of points in the xy plane satisfying f of xy equals some constant, which we usually use a c for. Now notice that the level curves are in the xy plane, so they're two-dimensional. And the reason we get this is because we make our function of two variables equal to a constant, so we only end up with x and y, and we don't end up with the z in the function. Here's an example from your textbook. We have the function z equals 100 minus x squared minus y squared. And in this figure, you see three typical level curves. So the first one, let's look at f of xy equals 75. This would give us this little circle, the inner circle, as the level curve. And here's why. What we do is we let our function 100 minus x squared minus y squared equals 75. This is how you always find level curves, is you pick a value for your constant and set the function equal to it. And then you want to solve it to be in a form that you know how to graph. So I'm going to subtract the 75 from both sides. And then I'll add the x squared and the y squared to both sides. So I end up with 25 equals x squared plus y squared, which we know is a circle of radius 5. And that's how we get that level curve, which is the circle inside of the other circles. So the level curve f of xy equals 75 projected onto the xy plane is that circle of radius 5 centered at the origin. Now here's another example. F of xy equals 0, so here we picked a 0 for our constant. We'll do the exact same thing, and we'll get this circle with a larger radius. In this case it will be radius 10, because we let our function 100 minus x squared minus y squared equals 0. Solve it and you get 100 equals x squared plus y squared, which we know is a circle of radius 10. And that's how we're getting these level curves, is by picking different values for the constant and just letting our function equal those values without the z variable. So instead of a z, you get a constant. So for each value of c in the range, we can calculate a different level curve for the function. Now the level curves, the reason we want to do this is because it can help us create what we call a contour map of the function, where we have the level curves on a two-dimensional plane, and then we have the different constants which would represent different z values. So if you go hiking and you look at a contour map of some terrain, you'll see the different level curves of the terrain, and by each level curve you'll see a constant that represents the elevation. So that's a good example of where a contour map and level curves are really used to display some type of useful information. Okay, let's look at a few examples that you might see in your homework, or similar to problems that you might see in your homework. Example 1 asks us to describe the set of all level curves of z equals the function square root of x squared plus y squared minus 4. So if we're trying to do a level curve, we want to let a constant, c, equal the square root of x squared plus y squared minus 4. To get rid of my square root, I'm going to square both sides. So I have c squared equals x squared plus y squared minus 4. Add the 4 to both sides to get all of my constants on one side and my variables on the other. So I have c squared plus 4 equals x squared plus y squared. So now, what we know about squaring a number is that it's always greater than or equal to 0. So what that tells us is that we have circles because of the x squared plus y squared equals a constant, and those circles always have either a radius 2 or larger. So this is all circles with radii greater than or equal to 2 because I'm adding a positive thing to the 4 in order to make the radius larger. Now, if I go to Wolfram Alpha and graph my function, this is what I get. This is actually the same function that we dealt with in example 1 of the first video for section 13.1. And we get this area in the center, which is the circle of radius 2, and you can see in the dark red that your function is actually not defined inside of that circle. It's not in the domain inside of that circle. So now, if I go to the contour plot, which is basically a plot of the level curves, I get all of these circles surrounding the circle of radius 2, and the circle of radius 2 is really a boundary of my domain, as we talked about in video 1. So here's the level curves or contour plot of the function. So to describe the set of all level curves, we would say all circles with radii greater than or equal to 2. That's how you would actually answer that question. And then to visualize it, you would look at the graphs. Okay, in this second example, we want to find and sketch the level curves of z equals natural log of 1 minus x squared plus y for the specific values of c, -1, 0, and 1. So let's do this one at a time. First one is c equals -1. So I plug in a -1 for z. So I have -1 equals natural log of 1 minus x squared plus y. To get rid of a natural log, we want to think about its inverse. E to the x is the inverse of natural log. So I'm going to raise both sides to the e, or rather do e to the power of each side. So I have e to the -1 equals 1 minus x squared plus y. Solve that for y and we get y equals x squared plus 1 over e minus 1. Now we know that e is just a constant value, approximately 2.72. And so we get y is approximately x squared minus 0.632. But our answer for the level curve will be this exact one, y equals x squared plus 1 over e minus 1. So that's our level curve for c equals -1. Now we want to graph it. So we have our x and y axes, and we just make the parabola that we got. So that's a typical level curve for this function, and in particular it's when the constant or your z value is -1. Okay, next value, c equals 0. We have 0 equals natural log of 1 minus x squared plus y. Do e to the power of each side. We get e to the 0 equals our function. So 1 equals 1 minus x squared plus y. Solve it for y, we just get y equals x squared. So that's our level curve when c equals 0. And here is the graph of it, f of x, y equals 0. So when the constant is 0, or when z is 0, you get y equals x squared. Last one for this example, c equals 1. We go through the same process. E to the 1 equals 1 minus x squared plus y. Solve for y. And there's our level curve for when the constant is 1. F of x, y equals 1. And to get an approximation for graphing, add e minus 1. So x squared plus 1.72. And there is our parabola. So you can see as the constant keeps increasing, you're just going to get a parabola that's shifted up. Notice that we're never making the parabola wider or skinnier. We're just shifting it vertically. So all of these level curves for this function are going to have that same format. There'll be a parabola and they'll just keep shifting up as the z value increases. On to our next example. We want to find an equation for the level curve of the function f of xy equals 2y minus x over the quantity x plus y plus 1 that passes through the point negative 1, 1. Now remember, for a level curve, we need a constant value. So what we'll do first is we'll use this fact that it passes through the point negative 1, 1, and we'll do that. We'll use that to help us find the constant value. So step 1, find the c value by plugging in the point that you're given, negative 1, 1. So I have my function at negative 1, 1 is 2 times 1 minus negative 1 over negative 1 plus 1 plus 1, which simplifies to 3. So that's my constant value, my c value. Now remember, to find a level curve, you just let your function equal a constant value. So step 2, the level curve is f of xy equals c. That will always be the step 2 in this process. So we set the function equal to 3, and then our last step will be to simplify. So we want to solve for y if possible, or get it into a format that we can graph. So we have 2y minus x equals 3x plus 3y plus 3. Just cross multiply. Add your x to both sides, subtract your 3y from both sides, and we get negative y equals 4x plus 3. So our level curve is y equals negative 4x minus 3. So this is the level curve in the xy plane. Remember, level curves are two-dimensional in the xy plane because we've gotten rid of the z by letting the z equal a constant. So that's the level curve that passes through the point x equals negative 1 and y equals 1. Now just to get an idea of what this graph looks like, let's go to Wolfram Alpha and graph it. And we get this 3D plot. So that's our actual function, z equals 2y minus x over the quantity x plus y plus 1. And then the contour plot, you can see it's all these linear functions. So you get this really cool visualization of what the graph would look like for all of these constant values of z. So if you projected your graph down into the xy plane, that contour plot would be what you'd see. Okay, now just a note about Wolfram Alpha. If you've never used it before, it's particularly good at showing level curves or contour lines for 3D graphs. For example, what I'd like you to do is just try using it. So pause the video, go to wolframalpha.com and type in plot z equals xy times the quantity x squared minus y squared all over the quantity x squared plus y squared. And when you get to the graph, click on the Show Contour Lines button, and it will display several level curves of the function. And you can try it with other functions too. So pause the video at this point, go to the website and just try it. Okay, hopefully you've tried out wolframalpha.com now. And this is what you should have gotten when you put in the input z equals xy times xy minus y squared, or x squared minus y squared, over the quantity x squared plus y squared. And contour plots will look like this. So you can see for different constant values of z, you're getting these hyperbolic looking functions that just kind of go according to these 3 lines or 4 lines that you have here. So now you have that tool available to you, the wolframalpha.com, anytime you want to visualize what's going on with your graph, with your 3-dimensional graph. Okay, last example in this video, we're going to go to a function of 3 variables. So a function of 3 variables is a rule that assigns a number to each ordered triple xyz in its domain. So now its domain is 3-dimensional, and so if I tried to plot the graph of a function of 3 variables, I would get a 4-dimensional graph, which we cannot picture. A lot of times when we're doing something like this, your 4th dimension would be something like time. For example, how does this 3D object change over time? And so that function could represent it, but we wouldn't be able to visually draw something that's 4-dimensional. What we can do, though, is we can look at what we call a level surface, and it's a set of points in 3 dimensions satisfying f of xyz equals a constant for some constant c. And a level surface will always be 3-dimensional. Now, for example, if you were looking at a function in physics where your 4th dimension or 4th variable was time, what we would be doing by looking at a level surface is we would be picking a fixed time. And so our constant would represent, for example, after 2 minutes, what would our object look like? So if c was 2, then you would be looking at what 3D object do we have when your time is 2 minutes. So that's an example of where you would use a function of 3 variables and look at its level surface in 3 dimensions. Okay, here's our example that's similar to a homework problem. Sketch a typical level surface for the function f of xyz equals x squared over 25 plus y squared over 16 plus z squared over 9. So a typical level surface will be of the form x squared over 25 plus y squared over 16 plus z squared over 9 equals a constant. And we know from the first unit of the course that this is the typical equation for an ellipsoid. So some egg-shaped 3-dimensional graph in our XYZ plane. Now to graph a typical level surface, what you want to do is just pick a value for c. I'm going to let c equal 1, and the reason is because that way I will be able to use the standard graph of an ellipsoid and know what the intercepts are. So if c equals 1, I'll get an ellipsoid where the x-intercept is 5 and -5, the y-intercept is 4 and -4, and the z-intercept is 3 and -3. So I go ahead and plot this, and then I'm going to put each ellipse on the graph. And now let me just outline this for you so it's a little more clear. It's this ellipsoid, so it's a three-dimensional object centered around the origin, where you have the different intercepts based on the denominators of your x squared, y squared, and z squared. Now if c were a different value, it would change those intercepts, but you would still have the same basic shape of your level curve. So that's what we mean by a typical level curve. Okay, so hopefully you have a good understanding now of level curves and level surfaces. We'll start out class next time by answering any questions you have on these topics.